So this is important historically to understand. Before about the 1960s, no one had ever observed this phenomenon. And if you think about the history of science, the 1960s are a very recent time period. It's a very new idea. And in some sense, it's an uncomfortable idea. Again, what it means, I'm repeating myself, but what it means is if you vary the initial term even slightly, it can lead to very different behavior. And let's see how we could see this in Excel. So I've started here with May's equation, just like before. I have R of n plus 1 equals, going back to an arbitrary alpha. So I do insert symbol alpha. And I'm going to see with different alpha values, does this hold? And the way that I'm going to do that is I am going to look at my time series that I've set up here. So as you may remember, a variable or a set of variables like this, where the expression depends on time, is called a time series. And I'm actually going to set up a second time series. And I'm going to make it so that my other time series is exactly the same, except the initial value is slightly changed. And so when I do this, I can use the fact that Excel has this beautiful copy expression. So I can copy the formula over from this column to the next column. And now I can also look and say, let's make this initial population of this other time series be the first value plus a very small. So these two initial starting values are very close. What it looks like as I go down is that the resulting behavior is very close. And this is probably what you would expect to see, right? You would expect that initially close terms lead to continually close behavior. Like you see there's very little difference between these. So when alpha equals 0.5, does this system exhibit sensitive dependence to initial conditions? Then the question is, okay, if I believe that this kicks in somewhere, where does it kick in? So I'm going to change my alpha value here. Instead of 0.5, now I'm going to change the alpha value to 3.9. And so now I've changed the alpha value to 3.9, which is a drastic change in terms of the initial parameter. And initially, just like before, you see that, okay, the initial starting values were similar when I changed this parameter. And now I'm going through and I'm looking and I'm saying, okay, as the system evolves, is this also similar? So do the two sequences, which are generated by the same equation, but slightly different starting values, behave the same. And at first they start out and they're fairly close. And they're fairly close. Whoa, what happened here? Uh-oh. They're getting further and further apart. So even though they started extremely close, by the 26th time step, the values are very different. Do you see that? Time for a graph. All right, let's graph it. Sounds good to me. So I'm going to select all of my information here. Oh, one thing you can do, I always just scroll, which is incredibly slow. Go to a chart, and I want a scatter. And oh boy, does that look chaotic. No, it's an absolute mess. And this was shocking to people. In the 1970s, when Mays presented this, it completely changed people's understanding of what a mathematical system could be. Because the idea was you have something in physics or biology, you expect it to be continuous. You expect it to be arrayed in such a way that small changes to the input produce wildly different. Is this interesting? I hope it is, because when I first learned this, my mind was blown. And I think that that was the way it was for most people in the scientific community.